Okay, I want to welcome everybody back to our live broadcast and everybody here. This is a sort of special time it's always Friday afternoon where we have the John Chappell Memorial talk, and we also call it in general the keynote speaker. We have today a person who we are honoring tonight at the banquet for a lifetime achievement award for his work over many, many, many decades. Just an incredible scientist. Many of us listen to him very attentively to his knowledge because it's very unique in the world. This also is a time where we remember all the people that started this organization, and it's really special to be back here, who has been involved or been with us for the last few decades. We had so many of the meetings here at the University of Connecticut, mostly because of Dr. Dominus Spencer, who was one of the first recipients of the Senyak Award, which we now call the Chappell Lifetime Achievement Award. And so it's really befitting, I think, of this organization being here at its philosophical roots, as our theme this year was listed. And those of us who do remember the great people who have passed on, this is quite an honor. Many, many great people have spoken in this position, and this is by no means any different. And we're really pleased to have today for the keynote speaker of the John Chappell Natural Philosophy Society, Dr. Bill Lucas.
Thank you, David, and for the leaders of the Chappell Natural Philosophy Society for selecting me to honor this year. The talk I'm going to give at this point is the role of the magnetic field in electrodynamics, in particular the atom and the nucleus. And the background for this talk is that when my second son was going to high school, he went to a science and tech high school, and you had to compete to get in. And then when he got in, he found that he had to do a 4-year science project. And he didn't know what to do. And I had just gotten back from a conference in Wisconsin, and he told me, he says, "Dad, I need a science project, and I want to do something that's significant." And I had met David Berkman there at this conference, and he was showing the model of the toroidal ring for electron. And I told him about it, and I said, well, why don't we see if we can do a science project on the atom if we use toroidal rings instead of point particles or spheres or something like that. And would that be significant enough for you? He said, yeah, I think that would be. And so I then contacted Dave Bergman, who I found out now when I met him that he lived in Alexandria, which is right near Washington, D.C., about 20, 30 minutes from my house, but I had never met him before. I met him at that meeting. And by the way, Dave Bergman and I ended up founding the organization Common Sense Science, which is similar in some ways to CNPS, and we have a lot in common. And so I got Dave Bergman to agree to officially be the mentor for the project, and then I was a helper for that. And so we started. I had been a judge for science fair projects at the regional level in the Washington area, which included a number of counties and all their schools. And having been a judge, I knew what judges were going to look for in science fairs. So I trained my son to do those things that he needed to do that a lot of people didn't do in their science fair projects. And I said, we need to do some experiments. And we're going to show some of those experiments we did to find out what the role of the magnetic field would be, in particular in the theory of the atom. Now, to get started, I want to talk a little bit about the version of electrodynamics that we currently use, what we would call the relativistic covariant Maxwell electrodynamic force. And notice that in particular it's defined in terms of A, the vector potential, and phi, the scalar potential. And if you were in Newton's time, Newton would say, what is a vector potential? I do my work in terms of the energy potential. And so he would wonder, he said, the vector potential isn't even a physical thing. Why do you have a theory in terms of something that's not even physical? But anyway, that's what I learned in graduate school and everywhere in my educational process. And so I want to then show you some characteristics of this approach. And so on the screen here, I have listed the assumptions and characteristics of this version of electrodynamics. One is it uses the point particle idealization. Two, it uses an idealized displacement current D in capacitors. Three, it assumes only action at a distance forces, no contact forces. Four, it assumes only linear field effects. That means lasers are impossible. We still teach this, by the way, in every college in the United States. But you can't explain why lasers work with this theory. You have to have another theory to explain how lasers work. It assumes static and induced fields are the same type of field. But William Hooper at the University of California in Berkeley has measured 14 properties of static and induced fields, and they are different. That has been published for more than 50 years, but we just ignore it. It assumes that there are no magnetic monopoles, but many companies in the world sell magnetic monopoles, and I have some in a box over there and let you come and do experiments with them. They're not to take home, but there you can do experiments with them, and you may have them on your refrigerator at home and you don't realize it. And so that's an interesting thing. Also, this version of electrodynamics ignores conservation of energy and momentum. And it assumes the arbitrary Lorentz gauge to uncouple wave equations. And it assumes the arbitrary Coulomb gauge to eliminate longitudinal fields. And I have meters at home that can measure the longitudinal field, and many devices have been made to create longitudinal fields. In fact, the first longitudinal fields were discovered coming off of radar antennas. And then last, it uses idealized special relativity theory, which is idealized because it doesn't take into account radiation, emission and absorption, and radiation reaction. And so it's incomplete. And so those are the things that we have discovered that are not too wonderful with electrodynamics at this time. The thing that nullifies the theory the most is that you can't have a vector potential if a magnetic monopoles exist. because it won't satisfy the requirements for vector potentials, because del dot B has to be equal to 0 to have that vector potential, and del dot B equals something if you have magnetic monopoles. And I'm going to show a short slide or a short video where someone takes a commercially available magnetic monopole and shows you how to make a free energy generator out of it. So we'll just take a look at that. I found it interesting. Oh, before that, oh, here we go. Oh, let's see. How do I make the video go?
Sometimes it won't launch. Let me see.
Oh. Wait, that's the next screen. We have to go back one. Maybe that. Here we go. Okay.
Now, most people are familiar with the basic north and south pole that all magnets have. Recently, people have tried to create a monopolar magnet with just a north or south pole. The problem is, if you break a magnet in half, you get two little magnets with north and south poles. Physics predicts that a monopole is possible, and in this diagram we see it in a dipolar configuration. The problem with monopolar magnetics, if it is a problem, is that it would make free energy and also perpetual motion possible, as seen in the motor here. I didn't think either of these things were possible until I found a magnet that would do it on eBay. Okay, with a normal bar magnet, opposites will attract opposites. A homopolar magnet is a little different. You wind up with one pole, and no matter what you do, it's the same pole on both sides. So this is a north pole monopolar magnet. You can see the south pole from the regular bar magnet is attracted to the face. And if I flip the face to the other side, it's attracted to the other side as well. So this is strictly north pole on both sides. Got a little paper clip over here. Now you can see which one's stronger, can't you?
They just turned the sound off.
Wait, hammer too.
So what he's doing is he's making a what's going to be a free energy generator. You'll see it in a second. Cutting a little groove in each of the nails so it can hold a coil there. And then he's winding the coil. And there it is with the two ends. Now he's going to mount the magnet.
All right, so here we go.
The two bases.
Got our basic little cradle here. Got the monopole here. It's going to stick to one of the nails a little bit. And then we've got our coil of wire. And the idea is, if we've got a monopolar field, it will induce a small current in the wire, which will create an opposing magnetic field. Anytime you have electricity moving through a coil, which is generated by a coil moving by a magnet, you'll have an opposing field. So it should cause this to flip around a little bit. We should actually have a motor of sorts, which is powered by nothing more than a magnet. So let's see if we get any luck. Just put it in the cradle here. Give it a touch. Whoa. And right off the bat we have it. Wow. A magnetically powered motor. Wow, and a powerful one at that too. Okay, so the really big test, of course, is going to be, are we getting a voltage generated from our free energy device? Put the copper coil back in the field, give it a little spin. Actually, it looks like it's ready to go on its own. Wow, look at that thing, it's already starting up. That is amazing. I'm going to touch one lead from the multimeter to the magnet and one to one side of the coil. And if we're getting a voltage, wow, look at that right off the bat. What is that, 2.53 volts, which is dying as the motor dies. Ha ha ha. And if we can get that balanced well and that magnet keeps that spinning in the field, we are getting completely free energy. Wow, we'll have to work on that cradle a little bit so that the copper wire doesn't come flying out of there. And just to demonstrate, it is copper wire, it's not magnetic in any way, unless it's in motion. And that is our free energy device.
Okay. Now I want to look a little bit at the theory of the Bohr atom. And the theory of the Bohr atom is an electron goes around in an orbit, and if it's in the outer orbit, it can instantaneously, with no passage of time, make the transition from the larger orbit to the small orbit and vice versa. Now, we can measure the time it takes, and it's instantaneous. So there's a problem there. The other problem, of course, is that whenever you have a charge going around another charge like this, it should be radiating energy not from changing orbits, but just continuously according to the laws of electrodynamics. And the only type of thing that could not radiate would be if you had a continuous ring of charge, in which case there's no change in the electromagnetic field as you go around. It's not required to radiate. So we see a number of things wrong with the Bohr theory of the atom. And you can see a number of things. In the work that I have done, which will be presented during the banquet, we'll find out that the electrodynamic force, when you derive it correctly from the empirical laws of electrodynamics, it requires that all material or building blocks of matter, and on a smallest scale, must consist of toroidal charge loops, or it doesn't get the radiation reaction term correctly. There are three terms for the radiation reaction. Two have boundary conditions. Those boundary conditions cause those other two terms, which we don't see experimentally, to evaluate to zero if all matter is made of toroidal charge loops. And so we'll see some of that this evening. And it turns out that combinatorial geometry combined with electrodynamics requires that every structure in matter must have spherical and chiral symmetry. And so that's interesting. Now on this next slide, if we're going to have that type of symmetry, then we want to look at what will be important. And basically what will be important is, let's see, laser flare, here we go. We have lines of longitude, or equatorial lines, sorry, and then we have, which are latitude lines, I guess, and then we have longitudinal lines. The latitude lines are parallel, but the longitudinal lines, which also form circles, they are different distance apart as you make the go further toward the pole. So there's a difference, and we want to consider how these toroidal rings which make electrons. Electrons consist of 3 toroidal rings, each with a charge of E over 3. We want to look at how these combine. And so we want to look at the field of combinatorial geometry. Now, I'll show you this slide. Okay, I've got 6 rings around the center ring. If I made that in 3 dimensions, how many do you think there would be? Anybody know? 12. So let's see if I have that. I think we have that slide. Oh, there's the 6, and the question is, we have a nucleus and we have electrons, and they apparently do not orbit the nucleus, but we have to have a mechanism to give off all these different emission spectral lines, and we have different excited states, and so we need to investigate that, and we're going to be doing it partially with combinatorial geometry, because this tells us, we have the idea that the electrons somehow exist outside the nucleus in what we would call shells. And shells are what you make when you're doing combinatorial geometry, the packing. So that's what we are interested in investigating. Now, when my son was doing his science fair project, we had to figure out how to determine this. Now, it turns out that when you have rings of charge, like in a coil, and you have current going through them, you can have a charge on the coil, and you can have a magnetic field coming out, and you have to balance the two. And so that's what you would expect. Here you can see the packing of 3-dimensional packing of the spheres. So the first experiment I got my son to do was this. We bought a large number of ring magnets, and we asked the question, if I have them all hanging together in a plane, and I use the force of gravity to keep the magnets apart, so that they don't all clump together, to represent the repulsion of the electric charge for electrons, then what does it look like when they come to equilibrium? Well, in this diagram here, the dark side, the dark rings are the North Pole, let's say, and the pink ones are the South Pole. And so you see that they form a plane, and they alternate North and South poles. And that's the only stable configuration that would work. And this would correspond to the ring of latitude, or longitude rather, that we saw. These would do that kind. So now we need to find the other type that are lines of latitude around the equator. So we'll go back now and see what we can do with that. Well, you probably are familiar with that. This is much more common than this one, but here is a picture of a shell of 8 magnets. Now, these are the equatorial lines, and then this going around the other way, there's 4 in each of those, and the other way with the longitude, there's 4 that go. And so we can see that here on the equatorial plane, the north pole of this ring is going toward the south pole of that ring, and the north pole of that ring is going to the south pole of this, and so it's north and south alternating all the way around, which is something that we need to notice. Also notice that if you hang all 8 of these by string from a board, which we have done, that they come to a particular geometrical arrangement, which is quite interesting. And another one to show you that, a little bit more complicated, here is a shell of 18 of these rings. And you see now the number of layers, I guess you'd call, is 3. 1, 2, 3. And on the previous one, we had 2, but we also had a smaller one of just 2 rings on one line. And so that if we were building a nucleus or an atom, we would have had 2 in the first layer, the second one would be 3, and then the next one would continue to increase. This would be outside the layer of 2 here, and we would have a number of 5. Now, if you have chiral symmetry, which the electromagnetic force has due to R cross V and R cross A terms in the force law, that chiral symmetry requires that the total structure has 1 layer, 3 layers, 5 layers, 7 layers, etc. And so when you start building them up, you discover, oh, I have just discovered from the magnetic properties that the size of the shells of the atom for which the Bohr atom was invented, 2, 8, 18, 32, and 50. So the first one is 1 great circle of 2 electrons. The second one is 2 great circles of 4 electrons. The third one is 3 great circles of 6 electrons. The fourth one is 4 great circles of 8 electrons. And the fifth one is 5 great circles of 10 electrons. And so that tells us how the structure of the shells of an atom, and even we'll find the shells inside the nucleus, that they are made to be specific sizes just due to the magnetic properties. Now, we want to consider another issue, and that is when we have these great circles with electrons in them, are they all bound with the same strength, or are they different? And so to do that, I had my son make a big board here, and he mounted 2 magnets here on wooden pegs, and then here he mounted, actually just one was a wooden peg. Here he mounted 4, and then here 6 and 8 and 10 correspond to each of the shells. And then he put a string down to a bucket with weights, and he measured how much weight or force it took to pull 1 magnet away from each of these size of rings. All the magnets are equal strength and equal size, but the size of the configuration is different. And so when he did that, we then obtained this data here. And so here's the 2, here's the 4, and the 6, and the 8, and the 10. So what do we find? Well, the binding of the 2 is less than the binding of the 4, and that's, the binding of 4 is stronger than the binding of 8, but the binding of 8 is, or 6 rather, is bigger than the binding of 2. So if I were making a nucleus, which has nothing in the center of it to hold it together, but I were just making shells, what one would expect is the smaller shells, like the shell of 2, would come apart and participate in the shell of 8 or 18. And you should be able to detect that in the structure of nuclei. And we'll see that you do. But in the quantum shell model, they always stay fixed in position and never change. we can also look at the atom. And so if we look at that, we can do the atomic radii versus atomic number. And we see that when we put one electron outside of a closed shell, lithium is the third one in the atomic number 3, we find that it's not tightly bound because it's outside a shell and it's repelled by the rest of the shell beneath it, and so it has a larger radius. And so we see that, and then as we get all the way down to completing a shell, you see it's a low point in each of these systems. So we have a lot of different measurements that show the shell structure. Here's another one. This is the atomic electronegativity, and you can see the same thing here. And but here you're measuring something different. The minimum electronegativity is given to the extra electron outside a closed shell, and you can see how that is working along. And then you also have the electron affinity, and you see how that changes with the shell structure. Now, I don't know if you know it, but NIST has measured the ionization energy to take away each electron of every known atom. And this next chart shows all of the data. And this data has been measured to 8 significant figures. And so here is the first shell of 2. You can see from the graph of it, in the Excel graph of the data that NIST provides. They don't provide the graph. I had to copy the data by hand and get it into this tremendous amount of data. But notice the shell of 2 and then a shell of 8. And then when we go to this next shell, which is going to be 18, we see a shell of 2 and a shell of 8 before we complete the shell of 18. And so you see that the shells preferred different size of shell because the binding energy was stronger, and the shell of 8 has a stronger binding energy than the shell of 18. And the shell of 2 is significant also. So what we see is we see the actual experimental data that supports the idea of the magnetic force controlling a lot of this. And we keep on going, we get up to the shells of 32. But when you get to the shells of 32 here, notice that you can't see all that substructure. It's the other shells are full for the atom, and it no longer makes that distinction. Although here, when we go to a shell of 18, we see the 2 shells of 2, and then we see the rest of the shells. They would go to 8, and then the rest to make up the 18 and then the 32. So what we see is we now have data that lets us almost see visually how the shells form, and we never had this data when we were doing our theories in the past. So this is since the year 2000 that we've had this kind of data. So we can make an electrodynamic theory of the nucleus, and in this one we have protons supposedly and neutrons, but the neutron may be an electron-proton pair. And the electrons I've shown as a bigger charge, a bigger ring here, but I must tell you that the ring is elastic. And so as you get it closer to a proton, it shrinks. I don't know exactly how big it is when you get it close enough to be in a nucleus, but it may be the same size as a proton. And so now let's take a look at what happens when we try to make a theory of a model of a nucleus. So we'll look at this next one. Here we're looking at oxygen 16, and the red dots here are the shell for electrons, and the protons are the blue shell. And notice inside the nucleus they alternate, blue, red, blue. And but if we go to the structure of calcium-40, where we have more protons, we find that we have, and more neutrons represented by a proton and electron, we find that we start out alternating shells, but then we have two shells in a row that are protons. What do these shells do? They repel one another, and they're not tightly bound. And so we have what we call the liquid drop model of the nucleus, and it's based on the fact that this surface is like a liquid. It's very loosely bound to the nucleus. And so we're able to predict where these liquid drop model will be applicable and where it will not be applicable. And we go to a more advanced one. Here's 118, and you can see that we have here alternating shells out to a certain distance, and then we have this liquid drop. Now, when these, if these particular nuclei are unstable and they decay, guess what? This part that's inside here stays together as a new nucleus, and this part out here that was weakly bound comes apart and forms stable, smaller nuclei. And so the liquid drop model, one of its best advantages was it could predict the final decay products of radioactive decay of various nuclei. And we can get the same thing from the electrodynamic model of the nucleus. And I think I have one more. Yeah. This is lead 208, and the same thing happens here. And so you can predict from the size of the outer liquid surface type shell, you can predict how many electrons there are, and what kind, how many protons and stuff there are, how many secondary decay products you'll have besides what's inside. And what's inside always comes out as one of the main decay products. Okay, now we want to look at the total binding energy, which we had measured earlier. And you can see that for 2 magnets in a shell, it's low. For 4 magnets, it's higher. For 6 magnets in a shell, 6 magnets times 3 layers would be 18. So this is a total number of 2, total number of 8, total number of 18, and this would be a total number of 32. And 32, they are more tightly bound than the 2, and that sort of thing. So what do you think you would find if you were looking at the nuclear density, and you want to look and see what it is for various elements inside the center of the nucleus? Well, here's the light nuclei up here. Oh, maybe I gotta show it here, wait a second. If I'm looking at the nuclear density, these are the light elements where I have the shell of 2 still there. But as I get to heavier elements, heavier nuclei, the shell of 2 disappears, and you see I have a shell of a lower density inside as the nucleus gets bigger, and it keeps dropping until I only have the most tightly bound shells. So that's an interesting phenomena, and it's the magnetic binding that determines that, not the electrical force, it's the magnetic binding. Okay, so we'll look at another, this is the Mayer nuclear shell model. This is a quantum model, and it is the first quantum shell model for the nucleus. and Mayer received a Nobel Prize, and she came from George Washington University in Washington, D.C. And she received a Nobel Prize for this in 1963. And if you look at the next slide, you can see the toroidal ring model of the nucleus. Notice now, as we start going and adding more and more nucleons to the nucleus, we start with a shell of 2, then we get a shell of 8, but the shell of 2 is gone. Then when we go to the shell of 18, we get the shell of 2 back. And then as we go to add more, we get the shell of 2, the shell of 8, and the shell of 18. And as we go, these are called magic nucleons. These are very stable elements. And then as we go to 50, we get 18 and 32, and the 8 and the 2 have gone away. And we get to 82, we've got a shell of 50 and 32, and no 18, no 8, no 2. And when we get to 126, we pick up a shell of 8 and 2 of 18 from what we had at 82. Now, what is going to happen is the shell model that Mayer did, it didn't take into account this. It would assume that this shell of 2 stayed there forever, and the shells of 8 stayed there forever, and the shells of 18. And so what happens, they don't get the magic nuclei correct. They predict the wrong one. And so if we go a little farther, this is the nuclear binding energy per nucleon. And this is a fit using the geometrical packing formula of the toroidal ring. And guess what? The fit, the error of the fit is 0.00025. If you look at the Goeppert-Mayer model and it's trying to predict the same thing, oh, they can't even do it. They can either predict the upper part or they can predict the lower part, but they can't predict both. And that's curve fitting for them. This is actual projection of many of the things. And the liquid drop model also can just do portions of this curve, the binding energy per nucleus. So we feel encouraged that the toroidal ring model enables us to predict the binding energy for 3,500 nuclear isotopes. Now I want to look at some other data. In the quantum shell model, it fails to predict the nuclear spin of a nucleus, the nuclear spin, and it fails to predict 1/3 of all nucleus that have a spin. 1/3, hundreds. Guess what? The toroidal ring model predicts 100%, because it's taking into account the fact that these shells back here are disassociated because they're not tightly enough bound. But the shell model puts that in here, and so they're going to get the wrong spin when they are doing it, because they're in the wrong shell. They're adding the electron, and so or the proton or whatever. So the difference in the models is spectacular. Then you have the magnetic force increases the stability of nuclids, and you can see this increase in stability by the length of the line of the number of stable and unstable nuclids that we've been able to see. So you can see here on this last one, it's about 15, whereas down here it's like 4 or 5 at the same atomic, same number of neutrons and atomic weight, I guess you would say atomic number. So it's it's very significant that we can predict that. But what I didn't have on here, I didn't have that slide with me, is there are islands of nuclear stability where there's nothing here, and then up here, at a much higher one, we have a little island of nuclear stability. And we have about 8 of those that we found. The nuclear shell model predicts 2 of them. We predict the 8 that have been observed and more that have not been looked for yet. But every one that we have projected that people have looked for, they have found. So we feel that's a very good sign. And that's the end of my slideshow, and it shows that the potential of the magnetic field of the toroidal ring model, it enables us to make a better theory of both the atom and the nucleus. I didn't go too much into the atom, but in my son's science fair project, they measured hundreds of spectral lines in the extreme ultraviolet for hydrogen and helium. And my son's model of the atom was able to predict 100% of all the lines they observed. And guess what? The Bohr model of the atom, the non-relativistic Schrodinger quantum model, and the relativistic Dirac quantum model predicted 0 of those lines. 0. And how many lines are there? There are just as many lines there as there is in the irregular emission spectrum that the previous theories of the atom had predicted. So not only does the model predict those lines, but it predicts the ones in the extreme ultraviolet. And that was what won him the grand prize at the International Science Fair. And so I wasn't planning on working in this field, even though I'm a physicist, but because my son had a science fair project and I didn't know how well it was going to develop. Whenever you do something new, it may be successful or it may be a failure. You may have a bad idea. You may have a good idea. And I was going on the advice of Dave Bergman and a fellow named Wesley from Germany, and they had been doing work on that. By the way, the ring model was not new with them. The ring model was developed by Parsons at the Smithsonian Museum, and they used to have a journal that they published, and he put that in. And if you go to the Smithsonian, they have his model. He made a model of the atom where he had rings of wire on gimbals, and so they could turn and twist. And he ran a current through them, and he built all of the atoms that we have in the periodic table with that model he had. And the chemists adopted the ring model, and they used it for more than 50 years, because with the ring model where the electrons do not orbit the nucleus, they're stationary, you could explain the structure of all the molecules, the angle at which they would bind together to form, different atoms would bind together to form a molecule. And when I was at University of Maryland, the chemistry department was only doing PhD theses where you measured the angles of the atoms in a molecule, and they were able to confirm this model of the, I forget the name of it now, this fellow, but anyway, he was very well known for having put this, you probably have seen it, it's like a dot model. You have let's say this is my atom, and then I have 2 dots here, 2 dots here, 2 dots here, 2 dots here. If I'm missing 1 or 2 of these electrons, and I have another atom over here that's got 1 extra one on the outer shell, it can just go in right there. But if I have two of them, it may replace that one. And so you can see the angles that it makes, and you're able to predict the structure of all the molecules that we make, including organic molecules, which are quite complicated and have spiral structure and that sort of thing. So it was quite a significant thing that he did, and so Parsons did that. And after Parsons did that, people at MIT started publishing papers on that, and then at Oxford University in Great Britain, they started publishing papers, and then they had the Copenhagen meeting in 1927 and decided to overrule all of that and go with the Copenhagen version of quantum mechanics. And that is what we currently teach. And the difference is one is a physical model and one is a mathematical model. And so the question is, which is better? And a lot of scientists like myself say, well, I like a physical model. I can see it, and I can understand how it works. And so that was what had happened. But there's a lot of people who are noticing problems with the quantum model, but so far the politics have not been right, and we're still stuck with the Copenhagen model of quantum mechanics. Okay, I'm through at this point. If you would like to ask some questions or make some comments, I'm open for that.
Okay, Bill, my question is, we see rings everywhere. Where did that come from? If the guy in the Smithsonian first thought of rings,
Yes.
What was the inspiration for rings?
The inspiration for rings came from is either Ampere or Faraday. He talked about atoms being made of magnetic molecules. And his magnetic molecule was basically a ring. But we didn't even have the concept of electron. Remember, that was in the 1860s and 50s. And then the electrons discovered in 1897 or something like that. So it was too early to develop that anymore. But the idea that magnetism would be controlling things and causing things to go together was there. But if you want to go back further, you can go all the way back to before the Trojan War, when Moshe, or Moses from the Bible, was reputed by the Greek natural historians as being the first proto-scientist, and he proposed the concept of the monad. There were only two types of monad, a monad and an antimonad, which is a lot like what Franklin uses, but trying to do a positron, electron, everything, and make things out of it.
Yeah, that's the monads.
They had the monad, and it had, it was very important, and the people who developed geometry and who were natural philosophers would put a sign over their academies, like our universities, and it said, "Let no one ignorant of geometry enter here, because they wouldn't know how to put monads together to get all the properties of matter." And that's a very interesting comment, but we ignore that today in the scientific community. I went all the way through the PhD in theoretical physics, never heard a word of that. I had to learn that by reading the documents myself. And I felt that was not very good.
Okay, we have some questions from the live stream.
Sure.
So Slobodan Nedik, he has two questions. He says, in your model, the proton and electron shells are interspersed, right? Because you showed the large diagram. Looks like you had
They're
electron.
built just outside of one another, yes.
Okay, that's
They're not.
very unusual.
They're in the nucleus. You have both electron and proton shells, but outside the nucleus, you only have electron shells, and that's due to the magnetic properties of the nucleus. It prevents any more from coming in.
Well, what's the difference between the electrons that are hanging outside the shells and the ones that are inside?
Well, one is they're bigger because they're elastic and there's not the same force on them, and but they're the same thing. When a nucleus decays and an electron comes out, we can't tell any difference between that electron and an atomic electron when we do experiments.
So the second part of his question is, having in mind Earnshaw's theorem, that Earnshaw's theorem says that there can be no stable arrangement of magnetic or electric forces. Do you consider different attractive repulsive forces for electric and magnetic interactions? I'm not exactly sure what he's asking there, but are you worried about Earnshaw's theory making this whole thing unstable?
I haven't paid a lot of attention to Earnshaw's theorem, but so I really am talking off my head at this point. But we do have a balance of forces. We use a tool called Mathematica, and Mathematica can construct a model for you, and with these toroidal rings, and calculate the force and actually put them in the equilibrium positions. And so that's a very nice property of Mathematica, and that's where some of those diagrams I showed you, various atoms and stuff for this shell structure and everything, that was how it was done.
Okay, we got a question from Pal. He asked, the sequence +2, +4, +6, +8 you use for electrons in concentric shells to get 2, 8, 18, 32, and 50. I use pattern in predicting the next prime. I wonder if there is some relationship between the two.
Well, the number 2, 4, that's where we were calculating the forces on the rings within a shell. You know, we had equatorial rings and we had longitudinal rings, and so that's your shell would consist of multiple ones of those. Like, you know, that's why when I was doing the slide, let's see if I can get back to it. I think I can get that. Let's see. Yeah, well, here's where, on this one here, you see the strength, relative strength of them, but that's only a sub part of the of it. Maybe there's another, I can't remember here.
So for your larger rings, like you had like up to 15 protons, would that be a similar
Well,
ring?
the shell would consist of 2, 8, 18, 32, or 50. Now, we don't get to the 50 for atoms, but we do get to the 50 for nucleus. And and these are the mechanism. This data here you see on the screen is the mechanism that justifies a total shell with so many toroidal rings and circles, great circles, whether they're equatorial circles or longitudinal circles. And so
I'm just wondering, would that be a circle of 50 like magnets?
no, it would be 5 layers of 10 in a ring.
So it never gets beyond the 10, basically.
Yeah, the total number in the whole shell does, yes. But that's, you see, when I showed the picture, well, it was way back there. Let's see if I can get to there.
So if
See
you're
here,
building at 50, it's actually...
this one right here, you see, the 2 is here, and the 4 is here, and the 6 is here, and the 8, but the total shell size is 2, 8, 18, 32, and 50. 50 is 5 levels, or horizontal levels of 10 electrons.
Okay, so it's always broken up. The maximum number of electrons that can be connected together would be 10.
Right. And, well, no, it's not the maximum number, it's the, they're not stable. They're not stable when they get bigger than that, yeah. I guess the atomic electrons might be stable, but the nucleus is not. And so that causes them to come apart.
Slobodan has a follow-on. He says, newest insights indicate 1/r³ proportionality for the magnetic force interaction. So they would be combined with the electrical 1/r². And so what do you think of that?
Well, 1/r³ produces a stronger force at small distances than 1/r². So that tells you why the magnetic force dominates over the electric force at small distances, which is what we have in the nucleus. Yes.
The free motion machine you demonstrated here.
Yes.
Can it be commercialized? That is built into a power station.
You can buy them on the internet, but yeah, in Germany
Where do we
there's
get that magnet?
In Germany there's a 5 megawatt free energy generator. 5 megawatts, but
That's getting something from nothing.
that's right. It uses no fuel, and it's based on the similar type of things, but it's built with bigger magnets. And I've seen it. It would fit in the front of the room here, and it produces 5 megawatts of power. And in the United States, they don't want you to do it. They'll go after you. If you go over to Germany and try to buy one and bring it through customs, they'll take it away from you and put you in prison. So you have to know what's going on. And let me tell you what happened. They started using these free energy generators in India. They were putting them in the villages that were too far away from any power stations. And they were not real big free energy generators, but they were enough to run lights and small motors and heaters and stuff like that in the villages. And guess what happened when they started doing that? The United States, Great Britain, and Saudi Arabia took economic sanctions against India for doing that, because before that, India was buying oil from those 3 countries to give out in these villages. And they saw that the end was coming. You wouldn't need it for your tractors, you wouldn't need it for your cars, and all that stuff would happen eventually. And so they took economic sanctions against India, and that was broadcast in all the major newspapers of India. In the United States, they said nothing about it. Yes?
I see no neutrons in your model.
That's right.
Does that mean that in nascent atoms or native atoms, in the natural environment, there are no neutrons in the nucleus?
When you look at the decay of the 3,500 nuclear isotopes and you assume conservation of energy, you find no evidence for the nuclear force or the weak force or for neutrons in nuclei. And we're measuring this to 8 significant figures, and if we assume that conservation of energy is true, then there's no evidence that they exist.
This means that the data presented here is so huge because for the last century or so, I mean ever since Chadwick came up with the idea of neutrons, neutrons made in the lab.
Yeah, neutrons do exist in the lab.
But it changes our whole concept of atomic structure and this layering of protons and electrons, and I find it mind-boggling.
Yeah, but you see this approach, if you look at my nuclear papers, I've brought a couple of them here, but there's many more on the internet. If you look at those papers, you see that we're able to predict the nuclear data better than it was ever predicted in the past. And I think that's a sign that our model is appropriate. But our model is based on the solution to the 6 empirical equations of electrodynamics, which predicts that when you get the radiation reaction term, we measure that in the lab, we know what it is, and there are 3 terms. One of them is exactly what we measure. The other two have boundary conditions on them, and the only boundary conditions that could cause them to go to zero is that the nucleus and the elementary particles are made of toroidal rings of something involving the field. And so that is quite important. That's covered in my book on the universal force, if you want to read it. And so it's there's just a lot of data now that seems to support this type of approach, and we're not advertising it. We have what's called the postmodern philosophy of science, in which we have silos for each field. So if somebody finds some data, like let's say I'm a geologist, and I find data showing the length of the day over the years from limestone coral, you won't see a thing about it in physics journals. Not allowed. That's only in geology journals. And so we've got this multiversity, multi-science. We used to have a university in which you look for the universal solutions, but we don't have it. And when I speak to presidents about it, they said we can't do that because the education framework from the Department of Education prevents us in America. We have to do it their way. And so that's a sad situation. And the only two colleges in the United States, one is Cedarville College in Ohio, and there's another one in Michigan. They're the only two that don't receive federal aid because they're religious-based, and they can teach that if they want, but their graduates are not recognized if they teach it or expose them to that information. So we live in a very controlled society, and I don't know the solution to that. It wasn't that way when we founded our country, but it is now. And how do you change it?
Thank you.
I have a question. You talk about field a lot. Can you describe that with your model?
What the field is? Well, the field has properties. I mentioned the fellow at Berkeley University. Can't think of his name right now. But he measured 14 properties of the 3 different types of electric fields and 14 properties of the 3 different magnetic fields. Now, in electrodynamics as currently taught, there's only one kind of electric field and only one kind of magnetic field. But when you go to the laboratory, you find that's not true. You find that there are 3 types of fields. There's the static field, there's the induced field, and there's the time-dependent field. And they all have different properties which you can measure in the lab. And so it's not as simple as you might hope, but you have to have some source of the electromagnetic field for the whole universe. And it's not matter and charges, because the matter and charges is made by soliton, which is a very long-lived standing wave in the field. And according to this approach, the concept of charge is a mathematical approximation. Just like if I had a cyclone or something like that here, and you were watching it, and you would see the funnel coming down to the earth, you could say, oh, look at that cyclone, it's about 2 feet in diameter, you know. But the weatherman looking out from satellite would look down and say, well, but look, all this clouds and everything are participating in that, and it's 150 or 200 miles across. Well, that's the same thing for these toroidal rings. They're like a what do you call a whirlpool or something like that, and they extend to a long distance. But you're just looking at the center part. And if I shine light through the soliton that's made in the swimming pool, for instance, I see a little disc. But if I look at the surface of the water, I can see that it's whirling around all the way to the edges of the swimming pool in every direction. And so what we do mathematically as an approximation is we just take that little disc or toroidal ring, or whatever you want to call it, and we say that is the particle and that's the size. But it's not true. Because the field at which it's made has tensile strength, the effects of that particle extend to great distances. And so that's what you can say. Now, if you were a Christian and Maxwell, Ampere, and Faraday were, they called the electric field, you know what they called it? The Spirit of God. Did they know what it was? No. But that fit what they thought, the way the universe works. But if you're not a religious person of that sort, you don't know what the source is. But the charges and the particles are not the source of the electromagnetic field. They are merely the solitons or standing waves in the field, and that standing wave has an effect around it, but due to the tensile strength of the field. But it's not there isn't really anything called charge. It's just that particular structure of the soliton.
Are you saying that everything is made out of this field, all matter?
Yes, all matter is made out of it on all size scales.
Bill, a question. Did I hear you say that the source for the electromagnetic field in the universe is not related to matter?
That's right.
Well,
but matter is a disturbance in the electromagnetic field, and we look at that disturbance as if the disturbance is producing the field, but that's not the case. And I gave the case so you could see that case more clearly when you have a cyclone or a tornado or a hurricane. You see that the eye of it is what we describe mathematically when we're talking about the toroidal ring or electron or something. When you see the eye of it, you say, oh, it's got a finite size, and all these winds and everything coming around it are due to that eye. Well, if I know about the weather, I say, no, the tornado, this big cloud thing, and the rotation of the earth and stuff like that, they're producing this funnel that you see. And the funnel is not producing the effects in the sky.
what I had in mind in asking that question was you've got a lake full of water, and you got funnels for that water to go down to cause generators to create electricity. It's the gravity that takes the water down that funnel.
And gravity is electromagnetic. Go ahead.
Well, is it? Okay. Then in that sense, I see what you're getting at in your assertion. I would interpret it much more simply that that is matter that is being moved by gravity,
Okay.
and that there's your source of electricity in a field.
In my papers on the table and in the talk I'm going to give during the banquet, I'm going to explain the definition of mass. It's an electrodynamic property. I'm going to explain many things based on what you have to be able to talk about if you claim that you have a universal force. And I don't claim I've done everything. And much of what I have done in presenting, other people contributed. Like I'm going to tell you when I do the summary of 60 years worth of work, I'm going to tell you, and you'll think, oh, you were brilliant to think that up. But the actual question is, or fact is, someone looked at what I was doing and said, you really should be doing this, that Newton put in his mathematical principles of natural philosophy. And I said, well, I've had that book, but I never read that part. And I read it, and I realized he's right. So, you know, everybody contributes a little bit, and you have to think about it over time, and you have to see what can be predicted. And I use a different scientific method, a scientific method that can falsify my theory better than any scientific method we currently use. And that is, if I use a false assumption, that can falsify my theory. And if I don't predict the data, that can falsify my theory. And since I have a universal force, I can't appeal to anything else. That's it. And so that's the situation. And I hope to finish publishing my book series. I have one on theory of elementary particles, electrodynamic theory of elementary particles, and the electrodynamic theory of the atom and the nucleus, and also molecules, including organic molecules, coming up. Yes, Franklin?
Okay, let's see here. Got another question from Slobodan. He says, so we as a group have to organize around the free energy topic, don't you all? Think so. Can you tell me the name of the German company you said it had a 5 megawatt generator?
I think I may, I don't have it off the top of my head, but I think I could send them, if you send me an email, I think I could probably send it to them. I have to find it.
Okay, folks, I think we're going to wrap that up. If you have any more questions, we can take them offline, but I want to thank you once again for this keynote talk. It was absolutely amazing. Tonight we're going to have the banquet where Dr. Lucas will be receiving a Lifetime Achievement Award. That will be starting at 7 o'clock. But once again, I want to thank you again for taking this honorable role and giving us a well worth talk in the history of this organization that fit in quite well. And congratulations. Thanks once again.